So I start. Yeah, I guess I start. Thank you for setting up everything. Thank you for joining here, and also those who are watching online later. And today I want to explain about confidential computing in Web3, especially how we do that at Flare. And yeah, like blockchains essentially are excellent and very good in transparency and making it everything verifiable, but sometimes you don't want to be public. Let's say, for instance, some couple of examples would be user data, business logic, some kind of specialized strategies, compliance checks, or cross-chain interaction, or some kind of sensitive off-chain data. You want to keep it private. You don't want to expose it. And then there is question, how can we keep this sensitive computation private? You can come in closer, otherwise you won't see the code later. So how can we keep this sensitive computation private, like how we execute something, but still have proofs and trust and verification on chain? And this is where Flare confidential compute, or TEs in short, comes in. And I will give you a short presentation, and then we will actually see the code, how it works behind the scenes. And before I go deeper into Flare confidential compute, let's take quickly a look what is Flare. So Flare is EVM layer 1, and it's designed around data. And the core idea is that contracts can access data from other chains, let's say prices, events, proofs, messages, and also Web2 data. And we can clearly say that Flare is blockchain for data if you need to process that kind of information. And Flare confidential compute especially extends this idea with data, because we can bring data on chain, not only read, but also write, and do it in sensible private manner, and have proofs back on chain. So basically results are relayed back on chain. And quickly about Flare confidential compute. So that, like I explained, adds this confidential execution layer to Web3. So basically sensitive work happens off-chain when you don't want to expose like private keys, API keys or something, or maybe some you have AI models, what are you running there, you don't want to expose, and also you have much more power than it is on chain. So you can access better machines for your tasks. And then everything is anchored back to chain. So there is integrity, identity, verification. So that comes back on chains. And developers can build applications where private stays private, but like computation still is in isolated environment. So that is the TE. And blockchains just receive sign actions, instructions what are sent to the chain, and then relayed back. And I think this is quite powerful, because we still get qualities of blockchain, and we can extend it and do it in actually very safe and trustless manner. And I want to explain that, stress that Flare confidential compute is still in latest development stage. It's on testnets. And yeah, so today I will give a sneak peek. It might change maybe slightly, but we are close to mainnet as well. So and right now we are getting like feedback. We had first hackathon, so yeah, I hope it will spark some feedback today as well, or tomorrow in this conference. And how it's kind of tied together, there is everything is Dockerized. There is T node, T proxy, which is relayed information from blockchain to Ts. But the main thing what developers need to worry about or need to develop essentially are Flare compute extensions. So we can say that these are small applications in T environment what runs inside these T machines in a secure enclosure. And thing is that these extensions, they don't have access to outer world, let's say. They have access only inside, so they pretty much get instructions in asynchronous manner, then they process these actions, and then they post results. So they don't have access to the blockchain itself. So that's behind the proxy, which signs all the transactions. And yeah, we can have like small comparison. So basically, smart contracts are deterministic and public, but Flare confidential compute extensions extend these smart contracts into workflows, into confidential private off-chain execution. So that's, I think, it's very powerful. And yeah, the mental model, I think, is public settlement but private execution. So public settlement, and thing is that all of this is with saved with the consensus, and basically all the instructions to E are relayed with 50% signature weight from data providers. So they you get same proof. I mean, same security as system Flare system itself, the network. And yeah, so that so we can think about these extensions, that those are like notary, that you can prove that some that notary kind of signs like document, but they not always expose what's in the document. So for instance, you want to know that if person can, you know, buy alcohol, let's say, very stupid example, but that's the most simplest one, and you need to know only if that person is above some kind of threshold age. You don't need to know their name, you don't need to know their exact age, you just need to know that that's like above this threshold. And notary signs, notary says, yes, you can sell to this person alcohol, and that's how these extensions work. So the proofs are still relayed back to the chain. And today I want to explain, I want to show a demo. So we look into more, and this demo is weather insurance. So basically, you came to this conference. Hopefully today won't rain, but actually yesterday and day before it was raining, and you buy insurance. So if it rains, you get money for taxi to come to this conference. So you don't need to come here, you know, soaking wet. So yeah, so that's the application I will be showing. So let me uh, so this is the front-end application I will be showing. We will go into details how it works behind the scenes, and a couple of things to set it up, as it is insurance application, is we need to have some kind of pool. In this case, that pool is by multiple people. It's just a pool, and it uses mocked ERC20 token for simplicity reason, because that's not the main point of this demo. But here is the you know, the real meat of this demo, is that we want to buy a policy, and Here I have two options, which is private and public, and we will look into today only in private. And how it makes everything private is that the signing mechanism is using ECIES mechanism. So basically, TE has a private key, and it exposes public key. So this is the very important how you can encode information and send to TE, and that TE has only this key, and then it can encrypt it. So that is very, very important. So it exposes public key. You can get this public key with GET request through the TE proxy for this specific TE extension, and then encrypt information, and then you know that no one else can encrypt this information because only the key is in TE. And important is that this key is in TE, so basically no one else can alter that. Otherwise, the hash of this TE is not correct, and all of these hashes are in TE registry on Flare blockchain, so you know that you are interacting. So basically, when you send interaction, we will check how it's from the code. This interaction won't be relayed to the TE, so the kind of integrity checks are not in place. But the thing is that TE, as it is trusted execution environment, is in secure enclave, and no one can, change it. So once you deploy it, it's there. And yeah, of course, there is a problem that what happens with the T goes down. So pretty much there is no state. There can be some workarounds, but I will not go into details in this demo. So we are actually currently exploring these mechanisms. Redundancy, that is, problem as well. Oops. And yeah, so then we can buy the policy. I will go into details, and then I created the first demo feature, which is getting live weather. So this application, where it gets weather, it gets from Open Weather Map API. We can argue if that is legit or something, but that's one of the best out there. And this is how we can, so the mental model how to get weather is from this Open Weather Map API. And let's say we want to get weather for Berlin right now. So what it does is that it constructs, I will jump into the code quickly. It constructs the request that it will be sent to TE. And as I explained, TE works in asynchronous model. So as you saw, there was small delay. So instruction is sent to TE. Basically, you say to TE, hey, please check weather. That's what you essentially say. And then TE does it work. In this case, it was a couple of seconds, but if you are working with like AI models or such kind of things, then of course it can take more time. So you need to see when this instruction has been processed. And we can see that currently it's almost 18 degrees and scattered clouds, so hopefully it won't rain today. So let's go into code. So here I will not show everything, but some parts. And code, of course, we have on our GitHub. I will show the post the link in my X as well. So everything is open right now. You can download and check it out later. But this is the smart contract, how when you call getWeather, interacts with this specific function. So what it does, I will make it a bit bigger. What it does is that it gets the TE from registry, and in this case we are getting just one T machine, so we are not using multiple, but for redundancy actually it could be more than one as well. The important one is that we are using extension ID, so each of these small applications have their own ID, but there can be multiple machines who are running this extension. We have cosigners feature as well, but in this demo I'm not using cosigners, so that's another layer of security. And then we are constructing the T instruction parameter. So essentially that is a struct which says what is the operation type. In this case that's weather, and what's the command. And then we are encoding a message. So message is arbitrary data what T will encrypt. I mean decode. And then we send that instruction to T registry, so we have all the necessary information. What's the T ID, what's the extension, what's the message, and then we send to registry. And then the Flare network, like validators, they see, okay, that's like valid instruction, all the hashes match, and then they can send, I mean, the TE proxy can pick it up and see, and I mean, relay to the TE itself. Come closer, then you can see code there. And let's go to the extension itself. In this case, extension is written in Go, but pretty much that's like web service, and you can use TypeScript, you can use Python, whatever language you like. And here we have a bunch of here is the config file where we are configuring these types, which is operation type weather, and then multiple commands. In this case, we just executed fetch, but then we will look into how we buy policy as well. And then the extension itself. So what it does essentially is that T proxy sends requests, and then it processes the actions. And in this case, we have just one action, which is weather. And then here we have a function which is processing the weather, and then multiple commands. And here, what's important is that in this case, weather fetching. So we can scroll a bit down, and what happens here, there are a bunch of checks. If we check if there is open weather API, if message is fine, but the most important here is that we are actually fetching the weather, and that lives in this utilities file. And what it does, it's actually not so interesting. It goes to open weather map API, and it fetches weather. Those who are in back, you can come in front, otherwise you won't see anything. And once that is done, then we have the report of the weather, and then we are constructing a result. And the T proxy signs this like result. So then we can see if that is that came from this T. But I think that's like very simple. But let's try and buy policy with this application, and then go into more interesting flow. So let's say we will buy, for instance, for Sunday. In this demo, of course, we can buy from backwards, but of course, in real application, it wouldn't be the case. And here, what it does, it approves these test tokens to buy the policy. That's not so interesting, but here all of this cryptic thing is that it tries to buy a policy in private manner, and we will go into code step by step. So let's hope everything works. So that executed, but now we need to relay back to chain the result. And I will go into step by step in code what is it is behind the scenes. So don't worry. And here we have Berlin. We haven't settled that policy, but let's go into code how it works behind the scenes. And so here we have smart contract, and let's go to to this function, which is buying policy in private approach. So basically, how it works behind the scenes is that once we specify the minimum rainfall, so basically, if it rains more than 1 millimeter, we will get the payout. But we don't want that everyone would see this minimum rainfall of millimeters. We want to encode it. And as we see in this list, that is hidden, like these millimeters is hidden. How it works behind the scenes is that we know the extension, that specific extension, we get the public key, and then we encrypt this information. So only the TE can encrypt it. And that is what we call here. So this is encrypted policy. And again, like I explained before, we get the T from registry. So in this case, we have just one, but we can have multiple machines running the same extension. We're not using cosigners. And we're executing operation type weather and command by. And we're sending this encrypted policy. And then we're sending to registry, so the validators can validate that everything is fine. The T hash is still intact, it's valid, and then it's relayed to the T confidential compute. And then we need to go to extension, and here let's jump to the buying policy privately. So what it gets here? It gets here the private by parameters. So remember, we encoded with private key. So basically, that decodes that information. So now because the T only can decode because it has this private key. And then it gets all the parameters like date, premium, payout, what we had here in this front end. So it gets all these parameters, and it creates commitment. So commitment, in this case, it is hashed information that we can relay back to blockchain. So then blockchain can reference what's in the T memory. So T is not exposing the this millimeter threshold. So it has the hash of this policy snapshot. So that is what is relayed back to chain. So then once it's done, it tells that, hey, I have the result, go and, we can see that that result is published. It's again in asynchronous manner because it can, here it's very, very fast, but it can take more time. For instance, if you are working with AI model predicting weather or something, then of course it takes time. And then secondly, you saw another transaction. So that is finalizing private buy. So pretty much anyone can execute that. And let's go into code what happens there. So when we're relaying back the private buy, we have the data from the T instruction result. we have the action ID, we have all the necessary information, and we have the signature of this TE as well. And then what it does is that it reconstructs this result. So we have the result data. Remember, that was hashed information. Then we have a submission tag, and then it's very important because it checks that from which TE this instruction came. So if you are trying to feed some malicious information, then the signatures are not, like working. So the signatures are wrong. So basically, that information could be signed with not correct key. And then we are saving this information on chain, like all these parameters, what's that payout, rain threshold, all that stuff. And then we are creating policies. Then we get the policy ID, and we are not exposing the in this list the what's the rain what we are buying the policy, so no one else can see it, or they can see what I'm working on. So we have only the proof on chain. And now we can go and settle this policy. So basically we want to get the payout. We know that it was raining. And again, I will show from the UI and then go into the code. So what it does, it requests the settlement for this specific policy, and then we get back the it's relayed to the T, and what T in this case will do, it will go and to Open Weather Map API and check if there was rain. And we can clearly see that there was 3.44 millimeters rain measured in Berlin this Sunday. Then we get back 10 tokens for our policy. So we bought for 1 and we got back 10. So this very simple how insurance works behind the scenes. But let's go into code where we have all the interesting stuff. And here I'm in smart contract. So first we start calling this function request settlement with policy ID. Then it gets the policy from the policy registry array, checks that there is this policy, it's not settled. We can settle after a specific unlock. In this application, I said that you can settle policies which are for previous day or after 6 p.m. Today. Otherwise, there is no data for today yet measured, rain. And then we are getting the TE, like we did before. And constructing the message. And in this message, we have policy ID. We have address who is settling this policy. Then we have date, latitude, longitude, and commitment. And remember that commitment is hashed information of this millimeters of rain. So we are still not exposing to publicly what it is, because maybe someone can intercept it in between before our policy has been settled. And then we send this instruction to TE. And I want to stress again that T's work in a synchronous manner. So you send instructions, they process it and return result. And then using proxy, you can see that, okay, this instruction has been processed. And then we send to the T registry. Again, all the network validators validate that this is correct. It belongs to the correct T. The code, the hash hasn't changed. There is a T machine running. All that is what network validators do. And let's go to extension. Again, I explained that this is in Go, but it can be in different language as well. So we need to find that this process whether settle. Yeah. So we have this function. So basically that gets the processing this settlement. So basically starting the settlement. Then we have a bunch of checks if we have API keys. And then we are decoding the settlement message. So then we get the latitude, longitude, basically location, date, all that stuff, which we are saving here. And we need to untangle the private terms. So now we have the hash, we have the terms commitment, we have them inside in the memory that no one else can see. These millimeters. So we take the hash and we get the correct millimeters. What we need to see if that insurance we need to pay out. So still is not visible to anyone. And then what it does is that it fetches day summary using Open Weather Map API to get the measure precipitation, I mean millimeters in rain, in short, from the API. And that happens here. And it's I would say nothing interesting. Is just a API get call with specific parameters and API key, which is not exposed as well. So this API key is only it's private in this T machine, so no one else can see it, no one else can read it. So that's for you. And I think yeah, it's very powerful. And I will talk a bit later other use cases where it could be even more powerful than this simple application. And once that is done, we have the revealed threshold of millimeters, and then we are creating the settlement result. What was what we get back from the Open Weather API. And then once that instruction I mean, this process has finished, it tells, hey, I have finished this action, and then we can get from T proxy, okay, this is finished, but we need to relay back that to chain, and that's why you saw two transactions. And in this second transaction is being called settle function. So we have the result data what comes from TE. We have action ID, and then important is signature, because signature what comes from the TE. And then if all the signatures match, so basically we derive the signer from this data. If that matches, so basically this message is from correct TE, then we can write this information on chain. And in this case, we are decoding the information from the result data, the policy ID, what's the millimeters, what's the date, and what is the revealed threshold. So basically, what we how we bought the policy at first place. In this example, I made that after the policy is settled, we can see what was in this policy, what the user specified. But of course, that could be actually private information as well. It's just for the demo that we can all see it. And we are updating the storage, so basically everything is on chain. So what you see in this front-end application, it comes from the chain. And yeah, here is the check. If it's private commitment, then we are revealing if everything is fine. And yeah, then we update the array on blockchain and emit settled event. So this is how it works from the code, and yeah, so we in this application, which is open source on our GitHub, I will post the link on my X, or you can find on Flare Network GitHub, and we can follow along everything, how we, for instance, bought this policy. So we can see that we bought for one token, and of course we can see that it's settled, and we get back 10 tokens. So it was raining, we came to the this conference, we're soaked wet, but at least we get money. So for those who joined later, this application what I'm showing is that if we come to this conference, it was raining, we bought policy before, and when we are, you know, wet, there is rain, we get money for taxi. So that's how it is. And the TE extension machine checks from the Open Weather Map API data. It sees that, okay, there was actually rain, and you get the payout. So that's short. I mean, maybe not so short from code perspective. I have a couple of slides, but then I will open for questions or recommendations. I hope it made sense. I'm not going over everything, and we have worked for this like for a while, and everything is Dockerized. So there is like what I mentioned, T proxies, T extensions, all that is Dockerized, and we have guides how you can start writing these T extensions. So you actually don't need to worry about everything. And later on, we are working with Google Secure Cloud. So this is the first partner we are partnering with, where you could deploy the T extensions, T applications, and we have multiple guides, multiple information how to deploy applications, and everything is still in development. It's on testnet, so it's fresh, and I'm happy that it worked today. So let's go back to the so here's the link for the demo, but I will post that on my X later as well. So you can find under Flare Foundation GitHub as well. And the time what I have left, I want to quickly explain what could be even more developer use cases, because this relatively simple application what I showed, it just goes and reads the information from API, and you are encoding this API key, which is not visible. But there could be even more use cases, like for instance private DeFi applications. Like you have some kind of risk scoring which is only you don't want to expose it. It's your tactic. Some kind of specific logics, like private routings or confidential portfolio checks. You need to go and check to some kind of API, or real-world applications. So that's actually very important as well. So you have some kind of maybe land registry or like state systems where you can verify that this information is actually true. So how we verified if weather, what was the weather information. Like regulated applications, for instance, like I explained, there is like compliance checks, and you don't want to expose sensitive information. For instance, people's age, people names, whatever it is. You just need to check if they are, for instance, citizens, or they own a property. So that can be possible here as well. Otherwise, it could be open, and not that we want to expose this information. Like data marketplaces, and very important, what we are working also, why we actually created this, and we are giving to anyone, is cross-chain automation or cross-chain communication. So we're working right now on cross-chain wallet, specifically with Bitcoin. So this is how you could control from Flare network, which is EVM chain, Bitcoin wallet. So you have the private key of the wallet, of Bitcoin wallet, and then you can initiate trades, you can read information, all that stuff. And the key is not exposed to anyone, only the code and proofs that you did something. And we call it protocol managed wallets. So basically, system protocol manages wallets outside chain, and I think it's very powerful, which could open even more eyes, in my opinion. And the thing is that all of this technology that I am showing right now, we are dogfooding ourselves. So basically, we're building products with this information, same APIs, same technology, and we are giving to anyone outside as well to build applications. And I think there could be some security trade-offs, so which I need to mention. For instance, like the key, you need to handle like failure. Basically, the T machine could go down, it can rotate. There could be, you need to think about recovery mechanism, maybe some multi-signature approach, how you store this key. Of course, the T machine itself, no one can change it. Otherwise, the hash is different. So basically, you see that machine has changed. But how you handle like keys, what's stored there, like to wallets, for instance, that of course is still up to you. That's not the technology what solves this specific problem. Yeah, and another use case is attestations of some information, external data. Like for instance, we attested that weather was measured at that specific millimeters, and then we got a payout with this application. And that's it. We are before time, so if you have any questions, I know that lunch is coming up as well. But if you have feedback, you can come and ask now. Later, I will be available throughout this week in this conference today and tomorrow as well. And still, this is very new technology. And we think that it will open many doors because there is privacy approach in blockchain. So that's how we can extend our smart contracts blockchain applications, and it opens many doors. Either communicating with other blockchains, getting information from other APIs, writing to other APIs. I know banking, weather, whatever APIs, and everything is everything could be there private, and you relay back only the validity proofs, so you don't expose private information. And importantly, you can get more powerful machine than it is blockchain, because blockchain is very limited. It's limited by gas, what kind of computation you can you have there. So let's imagine you can run like AI model in this trusted execution environment machine, which is in private, only for you. You do the computation with this model, and then only have the proofs, I mean the results back to the chain. So I think in this AI world, that's very important as well. I will be working on this idea later this summer, so you can follow on my X as well. I will post what we have, because we have multiple ideas how we can jump in this AI field and in trusted way. For instance, especially what happened in last week with Anthropic thing, that now we don't have in Europe this nice model because one person, we all know who, said that you cannot export that. And I think that shouldn't be the case. We can do better, that everything is kind of in just couple of people hands that you can make decision in 10 minutes. And yeah, I think it will open those doors as well, especially in AI. And in real world applications, like I explained, I think this is the missing piece what was in blockchain. We have been talking about that for years, but here you saw a working demo already. So thank you. If you have any questions, then ask right away. Don't be shy, or feedback as well. Thank you. Yeah, can you repeat for recording?
Okay. Sure. Is it working?
Yeah, I think so.
I don't know.
Test something.
Testing, testing.
Ah, okay. Now it's working, I think.
Okay. So, my question was, I don't know, I'm not sure, I'm not here.
It is working.
Okay, fine. So my question is, if you can go through the process of how the Go script is executed and also the end-to-end scenario. So I fork your repository, spin up a server, and put everything there. So that's sort of confusing for me.
Yeah, 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 yeah. I get the point. Right now is that you run it locally in Dockerized containers. So I have Docker containers here. So this is it's very small, but this is the weather insurance. It has the database and the proxy and extension running. So those are different services. So I will I will explain only about the flow. So basically, from front end, you start buying the policy. Let's go step by step. And how you run it? Right now, we have a repository which you can clone, and then you can set it up. There are guides on or DevHub also how to set it up. And I will be actually publishing about this specific use case most likely next week. So about this weather insurance as well. So there will be a guide how to run it. And how it works is that so you have a T extension running locally, but later this year we have guides how you can deploy to Google Secure Cloud. So there you can will be running this extension. No one can touch that one. Right now it's in testing phase, as I explained. And how it works is that we specify here the policy parameters. Then we call the smart contract. And smart contract has there is T registry on blockchain where all the T's have been registered and their hashes. And pretty much that is here we have System Explorer as well, where all the T machines are set up. So and, I'm working with this specific T machine. And then as TE, it processes these actions in a synchronous manner. So basically, it sits and waits, and then see, oh, one action came in, I will process that one. Then I processing that. I'm doing some magic. In this case, let's say I'm fetching the weather information. I have that one. Maybe it takes 1 minute, maybe 10 minutes, maybe 20 minutes. And then it relays the result back to the proxy. And then you need to actually fetch from the proxy that specific instruction has been finished because you have the ID when you send to the registry. And then when you have the result, then you relay this information to the chain. This was the, I explained that you see that these signatures match. Otherwise, if signatures don't match, someone can sign this information from different T, different machine, whatever. So you need to see that this information match and this is correct how it is in T registry. Because when you set up everything, you actually registering your T in T registry. We have a network level registry of all the machines and all the hashes. So that's the validity, integrity check how it is. It's not like sending out in the void. And then once you process that information, there is actually no specific need to send to the blockchain. It's just how the blockchain applications work. You have the proofs on chain. So this was the what I explained with how we store information. We don't expose these weather millimeters, but we have the hash of this policy. and that's the kind of the privacy aspect. So it's up to you how you store this information on chain, right? So yeah, so that's essentially it is that you through registry you send this instruction, then it's being picked up by TE in asynchronous manner, and then it's the result is relayed back, and then you fetch from the proxy. So yeah, I know maybe this is. I hope that's working. So I hope I explained, and all the guides are there. We have very simple sign extension guide on our dev hub. It's updated, it's up to date. Basically, how you can sign information, and pretty much you can, I know, commit to GitHub or something. You have GitHub key in this TE. So that guide is up there. I will be adding this guide later next week. So yeah, I hope I answered that question. Of course, this technology, per se, it's not easy, but we are hiding away because we are making it Dockerized everything, and you can spin up Docker, so you don't need to mess around. Actually, developers, you can read more what's behind the scenes, but you need to be working on extension code itself, and everything else is Dockers. Of course, it's not simple, but it's relatively straightforward how it works. But of course, I would like to get feedback if that guide is, understandable, because I want to improve that as well, all the flow. Yeah, good question. Thank you.
Thank you.
Any other questions, comments? Was it kind of clear? Maybe I want to ask audience: are you exploring trusted execution environments or private execution yourself? What's the theme out there? I know. Maybe show up hands who are like exploring trusted execution or private execution outside blockchain. Anyone? Okay, I see some hand. Maybe you can give.
Yeah, so we have our own solver infrastructure. So we're trying to like create an environment where we can do private swaps and stuff because we see a lot of value there. So yeah, I mean, a solver like touches so many infrastructure points from relays to swap environments. So we want to see like could be a hybrid environment where we use tight TEs for certain aspects and like ZK stuff for different aspects. So yeah, so
Yeah,
we see value for TEs for certain aspects of a model, but like kind of like
yeah,
ZK kind of execution stuff for privacy elements for different stuff. Yeah.
yeah. I would say this. Yeah, it's a bit different than ZK because this is private compute. So you get actually compute, and that's the essential. So we need to think about these machines because here was just simple example, but you can have maybe running some code for I don't know, half an hour, AI model, or maybe even more. So it can be such, and you cannot get that on blockchain. You cannot get even couple of seconds pretty much of execution, and this is how what opens doors, in my opinion, as well. This case, because we shouldn't limit ourselves just a couple of minutes. Of course, you pay for compute time. That's like obvious. For machine, you need to pay, but you get the proofs and you get the security aspect of blockchain, because all the network is still validators are proving that these instructions are valid. So yeah, I definitely would like to see more use case how you would use as well. Thank you. Anyone else, or we're ready for lunch? I guess that's it. Thank you for coming, and if you have feedback, then catch me later. And have a great Dappcon. Thank you.
Thank you.